Hello there, and welcome to Sleepy Science Vault. There is a question that human beings have been asking for as long as they have been capable of asking questions at all. Not a question about survival, or food, or shelter. A question with no practical answer. A question that serves no immediate purpose, and yet, somehow, will not leave us alone. The question is simply this: does it ever end? When you look up at the night sky, something happens that is difficult to explain. It isn't just wonder. It isn't just beauty. There is a faint unease that settles in, a feeling that you are standing at the edge of something your mind was never quite built to hold. That feeling has a name, even if we rarely use it. It is the feeling of confronting infinity. And here is the first thing worth knowing about infinity: it is not simply a very large number. It is not a billion, or a trillion, or a number so long it would take a lifetime to write. Infinity is something categorically different. It is the place where numbers stop making sense, where language begins to fail, where even the most disciplined human minds have found themselves standing in silence, reaching for words that don't exist. Our intuition, that quiet inner voice that tells us when something feels right, was shaped by the world we live in. A world of rooms and roads and horizons. A world where everything has edges. We evolved to understand things that fit in our hands, or at least within our sight. Infinity does not fit anywhere. It exceeds not just our perception, but the very architecture of thought itself. Throughout history, some of the greatest thinkers who ever lived have turned their attention to this idea, and many of them came away changed by it. The ancient Greek philosopher Zeno constructed paradoxes so elegant, so quietly unsettling, that they are still discussed more than 2,000 years later. His most famous asks a simple question: if an arrow in flight must first reach the halfway point, and then the halfway point of what remains, and then the halfway point of that, does it ever actually arrive? Mathematically, you are dividing a distance into infinite pieces. And yet the arrow lands. Something about infinity refuses to behave the way the rest of the world does. Aristotle tried to tame the idea by distinguishing between what he called potential infinity and actual infinity, the difference between something that could go on forever in theory, and something that is, right now, infinite in fact. It was a careful distinction. A way of saying, perhaps the infinite exists as a horizon we can approach, but never truly inhabit. Later, the mathematician George Cantor pushed further than almost anyone before him. He didn't just accept infinity as a concept, he studied it with the precision of arithmetic. And what he found was extraordinary. Not all infinities are the same size. There are, in a rigorously provable mathematical sense, infinities larger than other infinities. When this idea reached his contemporaries, some of them rejected it with a hostility that feels almost personal. Because infinity, when you stare at it long enough, has a way of doing something to you. It raises questions you didn't ask for. If the universe is infinite, truly, literally, without end, then what does that mean for the life you are living? What does it mean to matter, in something that has no edges and no center? These aren't just philosophical questions. They carry weight. People have sat with them in the dark and felt something they couldn't name. a kind of vertigo that has nothing to do with height. And yet, and this is worth holding on to, that feeling is itself remarkable. The fact that a human being, a creature of finite years and finite senses, can even conceive of the infinite, is extraordinary. Other animals do not lie awake wondering if the universe ends. We do. That capacity, that ache for the answer, is one of the most distinctly human things there is. Now, let's come back to Earth for a moment. Or rather, let's come back to what we can actually see. When astronomers talk about the observable universe, they are being very precise about something. They are not describing all of space. They are describing only the part of space from which light has had enough time to reach us. The universe is approximately 13.8 billion years old. Light, traveling at its absolute maximum speed, can only have crossed a finite distance in that time. Everything beyond that distance is, quite simply, beyond our reach, not because the technology doesn't exist yet, but because the information hasn't arrived. And in an expanding universe, much of it never will. The observable universe is an enormous sphere roughly 93 billion light-years across. That number is so large it loses meaning almost immediately. But here's what matters: that sphere, vast as it is, represents only a fraction of what likely exists beyond it. And in the mathematics of infinity, a fraction, no matter how large, is effectively zero. Think about that carefully. Everything we have ever seen, every galaxy ever photographed, every star ever named, every planet ever discovered, exists within a bubble that, compared to the full scale of what may exist, is indistinguishable from nothing. There is an edge to what we can observe. Not a wall, there is no wall. There is simply a horizon, the way the ocean has a horizon. Beyond it, the sea continues. We just cannot see it from where we stand. This horizon is not a failure of our instruments. It is a fundamental feature of reality. Light takes time to travel. The universe has a finite age. And those two facts, combined, create a ceiling on human knowledge that no telescope will ever fully break through. And so we find ourselves in an unusual position. We are creatures capable of imagining the infinite, living inside a universe we can only partially observe, orbiting a star that is one among hundreds of billions in a galaxy that is itself one among hundreds of billions more, all of it contained within a small, visible portion of something far larger than we can measure, or perhaps even comprehend. That isn't a reason for despair. It is, if anything, an invitation to a certain kind of stillness. The universe is under no obligation to be the size of our imagination. And perhaps that is exactly the point. The question of whether space is truly infinite is one of the most honest questions in all of science, because the honest answer is that we do not know. That might seem surprising. We live in an era of extraordinary scientific achievement. We have mapped the cosmic microwave background, detected gravitational waves, photographed black holes, and landed machines on distant planets. And yet the most basic question about the container that holds all of it, does it go on forever, or does it eventually stop, remains, officially, unresolved. This is not a gap that will be filled next year, or next decade. It may be a gap that is never filled. And understanding why that is the case tells us something profound about the nature of knowledge itself. What cosmologists can do is observe. They can measure. They can gather light from the farthest reaches of the observable universe and use it to draw careful conclusions about the geometry of space. And what those observations show is that the universe, on the largest scales we can probe, appears to be remarkably flat. Not flat in the sense of a tabletop, flat in the geometric sense, meaning that parallel lines, extended outward across cosmic distances, do not appear to curve toward each other or bend away. They stay parallel. This is a significant finding. But it does not tell us that space is infinite. What it tells us is that if the universe has a curvature, if it bends back on itself the way the surface of a sphere does, that curvature is so gentle, so gradual, that it lies beyond the reach of our measurements. The universe could be curved and closed and still be so vastly large that it looks flat from where we stand, the same way the Earth looks flat when you are standing in a field. So when scientists say the universe may be infinite, they are not reporting an observation. They are reporting a possibility that the data does not rule out. There is a difference, and it matters. There is also a deeper issue, one that physicists sometimes call the end-of-proof problem. Even if the universe is finite, we may never be able to confirm it. To know that space ends somewhere, or curves back on itself, you would need information from beyond your observable horizon. And as we have already established, that information cannot reach us. The observable universe is a sealed window. We can see everything within it with extraordinary clarity. But the glass itself cannot be removed. What lies beyond is not just unknown, it may be permanently, fundamentally unknowable. This creates a strange situation for science. One of the things that makes science work is the principle of falsifiability, the idea that a good scientific claim is one that could, in principle, be proven wrong. But the infinity of the universe may not be falsifiable in any practical sense. We cannot travel to the edge and look over it. We cannot receive a signal from beyond the horizon. The claim that space is infinite, and the claim that space is merely too large to measure, make identical predictions for everything we could ever observe. From the inside, they are indistinguishable. What this means is that when physicists write the word infinite into their equations, they are often making a modeling choice rather than a factual claim. Infinity is mathematically convenient. It simplifies certain calculations. It removes the need to define a boundary and explain what that boundary means. In the language of physics, assuming infinite space is often the cleaner option, not because we know it to be true, but because it produces useful results and does not contradict anything we have seen. This is not a criticism of physics. It is simply a reminder that our models are maps, and maps are not the territory. Infinity in an equation is a tool. Whether infinity exists in the actual fabric of reality is a separate question, one the equation cannot answer on its own. The mathematician in the room might push back gently here and say, but infinity is a perfectly coherent concept. It is well defined. It obeys precise rules. And that is absolutely true. The mathematics of infinity is some of the most rigorous and beautiful work human beings have ever produced. But mathematical coherence and physical reality are not the same thing. A shape can be perfectly describable in geometry without existing anywhere in the physical world. Infinity may be one of those things, real in the mind, useful in the model, and permanently beyond the reach of confirmation. Now, if we set aside the question of whether space is infinite and ask instead about its shape, we enter territory that is equally strange and considerably more beautiful. Most of us carry an unconscious assumption that space is simply a void, a blank, featureless container that things happen inside of. But general relativity, Einstein's theory of gravity, tells a very different story. Space is not a passive container. It is a dynamic structure. It curves in the presence of mass. It stretches and compresses. It has geometry, real, measurable, consequential geometry, and that geometry determines how everything within it behaves. On the largest scales, cosmologists describe the shape of the universe in terms of three broad possibilities. If the universe has positive curvature, it behaves like the surface of a sphere, extended far enough in any direction, you would eventually return to where you started. There would be no edge, but there would be a finite total size, the same way the surface of the Earth has no edge but has a measurable area. If the universe has negative curvature, it behaves more like a saddle. Space curves outward in a way that makes parallel lines diverge, and the total extent of space would be infinite. And if the curvature is exactly zero, flat, then space extends in all directions without bending, and infinity becomes at least geometrically plausible. Current measurements, as mentioned, point toward flatness. But there is a complication that changes the scale of everything, and its name is inflation. In the earliest moments of the universe, fractions of a second after the beginning, current theory holds that space underwent a period of expansion so rapid it defies easy description. Not expansion like a balloon being slowly inflated, but expansion so sudden and so extreme that the observable universe, in a vanishingly brief window of time, was stretched to a size vastly larger than it had any right to be. This process is called cosmic inflation, and while its details are still being refined, its general implications are striking. If inflation occurred, then the universe we can observe today, that 93 billion light-year sphere, represents only a tiny fraction of what inflation produced. The total extent of the post-inflation universe could be so large that even if it is technically finite and curved, the curvature per unit of observable space is essentially unmeasurable. It would be as if you took the surface of a sphere and inflated it by a factor of 10 to the power of many millions. The local geometry would look, for all practical purposes, exactly flat, not because it is flat, but because you are only ever seeing the most minuscule portion of the whole. This is one reason the flatness of our observations doesn't settle the question. Inflation would predict flatness regardless of the underlying shape. It is a kind of cosmic smoothing, one that erases the local signatures of curvature and leaves us with a universe that looks the same in every direction, at every scale we can access. And then there is topology. Geometry describes the local shape of space, how it curves at any given point. Topology describes something different, the global structure. how the whole thing is connected. It is possible, in principle, for a universe to be locally flat, to have zero curvature everywhere, and still be finite. If space is connected in the right way, you could travel in a perfectly straight line and eventually return to your starting point, not because space curved you back, but because of the way it is stitched together. Some topologies allow for this. A torus, the shape of the surface of a donut, is locally flat but globally finite and connected in ways that a plane is not. Cosmologists have searched for signatures of such a topology in the cosmic microwave background. The logic is that if the universe were small enough and connected in this way, the same patterns would appear in multiple directions of the sky, echoes of a space that wraps around itself. So far, no such signatures have been confirmed. But the search continues, and the absence of evidence is not yet the evidence of absence. What we are left with, then, is a universe whose shape is constrained but not decided, whose size is vast beyond imagination but not proven infinite, whose geometry points toward flatness but whose topology remains an open question. A universe that science has illuminated in breathtaking detail, and which still holds, at its largest scales, a mystery it has not yet chosen to give up. There is something almost restful in that. To know that the greatest question, the simplest question, in some ways, is still open, still waiting. That the universe has not been fully solved, and perhaps never will be. That there is always more darkness beyond the last light. One of the quietest and most persistent puzzles in modern cosmology is the possibility that space is not just large, but that it loops. That it folds back on itself in some subtle, hidden way, and that what we take to be the open expanse of the cosmos might actually be a kind of vast, repeating structure, like a room lined with mirrors, where every reflection looks like a new corridor stretching away into the distance. This idea belongs to the field of topology, and the specific search for it has a name: looking for topological ghosts. The logic is elegant. If the universe has a finite topology, if space wraps around in some direction, the way the surface of a torus does, then light would eventually travel all the way around and return. Given enough time and enough distance, the same object would appear to us in multiple locations on the sky. We would see, in different directions, what are actually the same structures, the same ancient patterns of hot and cold gas, echoed and repeated like a signal bouncing between walls. The best place to look for these echoes is the cosmic microwave background. This is the oldest light in the universe, radiation released roughly 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely for the first time. It fills the entire sky, a faint, nearly uniform glow at microwave frequencies, patterned with tiny temperature fluctuations that carry the imprint of conditions in the very early universe. If space wraps around itself, certain patterns in that background radiation should repeat. Specific circles on the sky should match other specific circles, their temperature patterns identical, because they are, in fact, the same circle, seen from two different angles through a folded space. Cosmologists have searched for these matched circles carefully and with considerable ingenuity. So far, they have not found them. The patterns in the microwave background show no confirmed signs of repetition, no ghost circles, no topological echoes. This doesn't prove the universe is infinite. It sets a lower bound on the size of any possible repeating structure, meaning that if space does wrap around, the distance at which it wraps must be larger than our observable horizon. And if the wrapping scale is larger than what we can see, it is, for all observational purposes, as good as absent. We cannot test what lies beyond the horizon, and so the topology of the full universe remains, once again, beyond reach. This connects to something deeper, a structural feature of infinite space that is easy to state and genuinely difficult to sit with. In a truly infinite universe, there is no edge to approach, and therefore no edge-based test to perform. Every measurement we can make is made from inside. There is no vantage point outside the system. There is no Archimedean point, that old philosophical concept of a fixed, external position from which to observe the whole. Archimedes famously said that with a long enough lever and a place to stand, he could move the earth. But in an infinite universe, there is no place to stand outside of it. There is only inside. This has consequences that extend beyond the merely technical. In a finite universe with a center, the idea of a special place makes sense. There would be a point from which everything else could be measured, a cosmic origin to which all coordinates ultimately refer. But in an infinite universe, or even in a universe that is simply very large and without a preferred direction, no such point exists. Every location is equivalent to every other. No point in space is more central than any other point. You are not at the edge of the universe, but neither is anything else. There is no edge. There is no center. There is only the local, the immediate, the here, and then more space in every direction without distinction. This is called the cosmological principle, and it is one of the foundational assumptions of modern cosmology, that the universe, on large enough scales, looks the same from every point within it. Uniform. Isotropic. Without a special place. In some ways, this is a deeply humbling idea. It means that the location you occupy, the precise coordinates of the planet you are on, the galaxy you are in, carries no cosmic privilege. The universe did not arrange itself around you, or around anything. There is no throne at the center, no axis running through the whole. Just space, extending outward with remarkable evenness, indifferent to the question of where the middle might be. But there is another way to hold that same idea, and it is considerably more generous. If there is no special place, then every place is, in a sense, equally valid. Every point in the universe is as central as any other. From where you are standing, or lying, right now, you are, by the logic of an infinite and centerless cosmos, at the center of your own observable universe. The horizon extends equally in every direction around you. The oldest light reaches you from every angle. You are not peripheral. You are not marginal. In an infinite universe without a center, every point is the center, and that includes the exact location you happen to occupy at this moment. And then there is the question of the outside. In everyday experience, everything has an outside. A room is walls, and beyond the walls, a building. A planet has an atmosphere, and beyond the atmosphere, space. We are so accustomed to this structure, thing, then boundary, then beyond, that it takes a genuine effort to imagine something for which it simply does not apply. But an infinite universe has no outside. There is no beyond. Not an unreachable beyond, not a beyond we lack the instruments to access, just the complete and total absence of the concept. The universe is not a thing inside something else. It is not surrounded. It simply is, in all directions, without enclosure. This is one of the places where language fails most visibly. Every word we have for space implies a container, a boundary, a context. The universe is the context for everything else, but it has no context of its own. There is no frame large enough to hold it. No map with a legend that includes the edge of all things. Now, if those ideas have been quietly loosening something in your sense of what the universe is, what comes next may loosen it a little further. Most people carry a mental image of the Big Bang that goes something like this: a single point, an explosion, and then expansion outward in all directions, like a firework frozen in slow motion, the galaxies sailing away from a common center toward an open and waiting darkness. It is a vivid picture. It is also, in important ways, misleading. The Big Bang was not an explosion in space. It was an expansion of space. And that distinction changes everything. In the standard cosmological model, there was no pre-existing void into which the early universe expanded. Space itself came into being, or more precisely, the space that exists today was, in those first moments, compressed into an extraordinarily hot, dense state. But here is the part that most popular descriptions quietly omit: if the universe is infinite today, then it was already infinite at the Big Bang. Let that settle for a moment. Infinite space does not become infinite through expansion. It is either infinite or it is not. If the universe is truly spatially infinite right now, with space extending without end in all directions, then at the moment of the Big Bang, when everything was compressed to extreme temperatures and densities, that infinite space was still infinite. It was just infinite and very, very hot. And very, very dense. Uniformly so. Everywhere at once. Without a center. Without an edge. The Big Bang, in this picture, was not a local event in a larger space. It was a condition that applied to all of space, simultaneously. The entire infinite extent of the universe, at once, was in that primordial state. And the expansion since then has not been a spreading outward from a point, it has been a stretching of space itself, everywhere at once, in every direction, with no location more original than any other. This is what physicists mean when they say the universe has no center of the Big Bang. There is no point you could travel to and say, here is where it started. It started everywhere. Every cubic meter of space that exists today is equally the site of the origin. The beginning was not a place. It was a moment, and it happened everywhere simultaneously. For a human mind shaped by ordinary experience, this is genuinely difficult to absorb. We are used to events that happen somewhere. A fire starts in one room. A storm forms over one ocean. Even the most powerful natural phenomena have a location, a point of origin, a place from which they spread. The Big Bang refuses this framework entirely. And so the word birth, when applied to the universe, requires careful handling. What was born? Not a thing inside something else. Not a bubble in a pre-existing void. If the universe is infinite, its beginning was not the creation of a bounded object. It was the beginning of time itself, of the conditions under which anything at all could happen, spread across an infinite stage that had no before, no outside, and no edge from which to observe the whole. That is a sentence that repays sitting with. There was no before. Not a long, empty before, stretching back into a darkness we cannot see. Simply the absence of the concept. Time, as a thing that passes, began. And with it, space, matter, energy, and eventually, after billions of years of patient arrangement, the possibility of a mind that would lie awake at night, wondering how any of it started. There is a problem that lurks quietly at the edge of almost every attempt to reason about infinity, and philosophers have given it a name that suits it well: the infinite regress. The worry goes like this. If you ask what caused the universe, and someone offers an answer, you can always ask what caused that cause. And whatever answer comes next, you can ask again. And again. Each explanation demands a prior explanation, and there is no obvious place to stop, no bedrock you can point to and say, "Here, this requires no further justification." This simply is. It is an uncomfortable loop. And throughout history, different traditions have handled it differently. Some proposed a first cause that was itself uncaused, a prime mover, a necessary being, something that existed by its own nature rather than by virtue of something else. Others argued that the regress is not actually a problem, that time itself began with the universe, and so the question of what came before is simply malformed, like asking what lies north of the North Pole. Still others have sat with the discomfort and declined to resolve it, accepting that at the outer edges of explanation, human reasoning reaches its natural limit. Modern cosmology doesn't dissolve this worry. It redirects it. In the framework of an infinite universe, the question of ultimate origin becomes even more layered, because there is no single point to assign as the source of everything. If the Big Bang was a condition that applied to all of infinite space simultaneously, then the question of what preceded it, or what produced it, applies equally everywhere. There is no local answer. No manageable starting point. The regress, if it exists, is infinite in extent as well as in depth. What physics does offer, in place of a final answer, is a description. Not a cause, but a structure. Not a reason, but a remarkably precise account of how things have unfolded since the conditions we can measure began. And within that description, infinite space appears not as a dramatic revelation at the end of a story, but as a background, a quiet, featureless stage on which everything else takes place. This is an important shift in framing. Infinite space is not a wall at the edge of reality. It is not a boundary you approach and eventually reach. It is simply the context, everywhere present, nowhere specially located, making no particular demands on the events that occur within it. It does not glow. It does not announce itself. It is just there. In every direction. Without end. And within that background, structure has emerged on a scale that requires its own kind of patience to appreciate. When you look at the distribution of galaxies across the observable universe, what you see, at first glance, is a kind of organized chaos. Galaxies clustered together, strung along enormous filaments, separated by vast empty regions called voids. It looks almost biological, like a microscopic image of a cell or a neural network. Cosmologists call this the cosmic web, and it is one of the most striking features of the universe at large scales. But there is a threshold beyond which this web smooths out. At scales of roughly 300 to 400 million light-years and above, the universe becomes statistically homogeneous. The clumping disappears. The filaments and voids average out into something uniform, the same density, the same composition, the same properties in every direction. This is the scale at which the cosmological principle actually holds. Below it, the universe is beautifully structured. Above it, it becomes, to a very good approximation, a featureless sea. Now, here's the question that infinity introduces. Does that structure, the cosmic web, the filaments, the voids, repeat? Does it continue, beyond the observable horizon, without end? In a truly infinite universe, there is no reason for it to stop. The physical laws that produce the web here would produce it everywhere. The same forces of gravity and dark energy, acting on the same initial conditions replicated across infinite space, would generate the same broad architecture in every direction, forever. This means that if you could somehow travel beyond the observable horizon and look around, which you cannot, but bear with the thought, you would likely see more of the same. More filaments. More voids. More galaxies arranged in that same intricate, web-like pattern, fading upward into homogeneity at large scales, resolving downward into rich structure at smaller ones. The universe would look, in all directions, like a vast elaboration of what we already see. Not because we have observed it, but because the mathematics of an infinite, uniform beginning would produce nothing else. Dark energy adds another layer to this picture. The force that is driving the accelerating expansion of the universe, whatever it is, and its nature remains one of the deepest open questions in physics, appears, from all observations, to be perfectly homogeneous. It does not cluster. It does not vary. It fills space uniformly, with the same density everywhere we can measure. In an infinite universe, that uniformity would extend without limit. Dark energy would be everywhere in equal measure, pushing space outward at every point simultaneously, an invisible and uniform pressure applied to the whole of an infinite stage. This is one of the features of infinite space that cosmologists find both elegant and quietly troubling, the absence of any preferred direction. In a finite universe, certain directions might be special. If space curved back on itself in one axis but not another, or if the origin of the universe were concentrated in one region, there might be directions of the sky that look different from others. But in a flat, infinite, homogeneous universe, no direction has any advantage over any other. North and south, in the cosmic sense, are identical. The universe has no up, no down, no left, no right. Every axis is equivalent. Every compass point leads to the same kind of landscape, forever. Physicists call this isotropy, the same in all directions, and it is one of the most precisely tested properties of the universe. The cosmic microwave background varies in temperature by only about 1 part in 100,000 across the sky. The universe, at the largest scales, is extraordinarily smooth. And in an infinite universe, that smoothness is not a local accident. It is the global condition. But this isotropy, this homogeneity, creates a subtle and somewhat vexing problem for science. It is called cosmic variance. When cosmologists study the large-scale structure of the universe, they are, in a sense, working with a sample of one. There is only one universe we can observe, and we observe it from only one location within it. We cannot step outside and take a different measurement. We cannot run the experiment again with different initial conditions. We have exactly one data point at the very largest scales. This means that for the biggest structures, the largest patterns in the cosmic microwave background, the widest features of the cosmic web, we have an irreducible limit on how precisely we can measure them. Even if our instruments were perfect, the fact that we occupy a single position in a single realization of an infinite universe means that some measurements are subject to an uncertainty we can never reduce. We are seeing one corner of one room in an infinite building, and drawing conclusions about the architecture of the whole. In an infinite universe, there is also a related difficulty that is more philosophical in character. In a truly infinite space, containing infinitely many galaxies and stars and regions of all possible conditions, the concept of a cosmic average becomes problematic. An average requires a finite set of things to average over. If the set is infinite, the average may not converge to a well-defined value. Certain quantities that physicists would like to treat as global properties of the universe, an average density, an average temperature across all space, may not be mathematically well behaved if the universe is truly infinite. This is not just an academic concern. The assumption of homogeneity, of a well-defined average state, underlies much of modern cosmology. If that assumption breaks down at some level, if the universe's infinite extent means there are regions, far beyond our horizon, where conditions are so different that no average can represent them, then our models may be missing something fundamental. Not wrong, necessarily, but incomplete in ways we cannot currently see. And underneath all of this lies the deepest of the symmetry assumptions, the quiet bet that physicists make every time they write down an equation and expect it to hold universally. The laws of physics, as we understand them, are the same everywhere. The speed of light, the charge of an electron, the strength of gravity, these do not appear to vary across the observable universe. The same mathematics that describes a collision in a particle accelerator on Earth describes the nuclear reactions in a star a billion light years away. The universe plays by consistent rules. In a finite universe, this is still remarkable. In an infinite universe, it is something more. It means that the same elegant handful of laws governs an unbounded expanse, that whatever logic underlies the behavior of matter and energy, it applies not just locally, not just within the reaches of our observation, but everywhere, in every direction, to every particle in every field, without exception or diminishment, for as far as space extends. Which, if the universe is truly infinite, is a very long way indeed. There is something almost meditative in that thought. Not the scale, which resists imagination, but the consistency. The quiet, reliable uniformity of the rules. Wherever you go, wherever anything goes, the same logic applies. The same causes produce the same effects. The universe does not change its mind. In a cosmos without edges, without a center, without an outside or an average or a preferred direction, that consistency is perhaps the most grounding thing there is. Not a wall to lean against. Not a floor to stand on. Just the steady, unchanging character of the laws themselves, extending through infinite space like a thread that never breaks. The laws of physics do not diminish with distance. This is one of the most quietly extraordinary things we know. A photon released from a galaxy 10 billion light-years away obeys the same rules as one emitted by a lamp in a quiet room. Gravity curves space in a distant cluster the same way it curves space around the sun. The mathematics developed in laboratories on a small planet in an unremarkable corner of the Milky Way turns out to describe, with stunning accuracy, events occurring across the full breadth of everything we can observe. In an infinite universe, the implications of this are hard to fully absorb. It means the same logic, the same compact set of laws, the same constants, the same relationships between force and mass and energy, governs an expanse that has no limit. Not governing it up to a point, not approximately true in distant regions. Governing it completely, everywhere, without exception. The universe is not just large. It is large and internally consistent, all the way down and all the way out. That consistency is worth carrying forward, because what comes next is where the story begins to change character. For all its uniformity and order, the universe has a feature built into its present moment that places a ceiling on what any observer can ever know. And that ceiling is not a failure of technology. It is written into the structure of space itself. We have already touched on the idea of the observable horizon, the boundary beyond which light has not had time to reach us. But there is a second horizon, subtler and in some ways more final, that arises not from the age of the universe but from its expansion. The universe is not just expanding. It is expanding at an accelerating rate. Galaxies that are sufficiently far away are receding from us so quickly that the light they emit will never reach us, not because it is too slow, but because the space between us and them is stretching faster than the light can cross it. These galaxies are not moving through space away from us. Space itself is growing between us, and growing faster than light can traverse. This means that right now, in this moment, there are galaxies that we can currently observe, whose ancient light has already reached us, that we will never hear from again. As the expansion accelerates, their signals will redshift into silence. They will fade. And eventually, in the far future, the sky will contain only the light of our local group, the gravitationally bound cluster of galaxies that includes the Milky Way, while everything else recedes beyond permanent, unreachable darkness. The universe is, in a sense, slowly closing its doors. This is what physicists mean by a causal horizon. It is not just a limit on observation. It is a limit on influence, on connection, on the possibility of interaction. Beyond a certain distance, no signal you send will ever arrive. No message, no force, No consequence of any action you take will ever reach the regions beyond that boundary. And they cannot reach you either. You are causally isolated from them, not temporarily, but permanently. An infinite universe full of events, most of which can never affect you and which you can never affect. In this sense, infinity does not grant access. It grants separation. The vastness of space is not an open invitation, it is an architecture of irreversible isolation, built into the geometry of an accelerating cosmos. And even within the regions we can observe, information has its limits. Light takes time to travel. By the time the light from a distant galaxy reaches our telescopes, the galaxy that emitted it may no longer exist in anything like the form we see. We are not observing the universe as it is. We are observing it as it was, at many different moments simultaneously, the distance of each object corresponding to a different point in the past. The night sky is a kind of temporal collage, layered with light of different ages, from different eras of cosmic history, arriving all at once. As expansion continues and horizons tighten, future astronomers, if they exist, will find themselves with less information available than we have today. Galaxies currently visible will have receded beyond the horizon. The evidence for cosmic expansion, the patterns in the microwave background, the diversity of galaxy redshifts that allowed us to reconstruct the history of the universe, all of it will fade or vanish. A civilization born in the far future, in an otherwise identical universe, might look out at a sky containing only a handful of galaxies and conclude that the cosmos is small, static, and young. They would have no way of knowing what they were missing. The evidence would be gone. This is sometimes called the end of cosmology, not a dramatic conclusion, but a slow erasure. The universe will not announce it. The sky will simply, over immense stretches of time, grow darker and quieter, until the questions we ask today can no longer be answered because the data needed to answer them no longer arrives. And time itself, in an infinite universe, reaches in directions that make even the largest spatial scales feel modest. If the universe continues to expand and cool, and current physics gives no reason to expect otherwise, then the very far future leads to what is called the heat death. Not a violent end, but a gradual equalization. Stars will exhaust their fuel. Galaxies will dim. Black holes will slowly evaporate through a quantum process so slow it makes the current age of the universe look instantaneous. Matter itself may become unstable over timescales so long they exceed any number with a common name. And eventually, if time continues indefinitely, the universe will approach a state of maximum entropy. A condition of total equilibrium, where no further useful work can be done, no temperature gradients remain to drive any process, no complexity can form or persist. It will not be silent in the human sense. It will simply be finished. A vast, cold, dark expanse, maximally disordered in thermodynamic terms, extending through infinite space without event, without structure, without memory of everything that came before. This is not a comfortable image. But it is worth holding, because what comes next is one of the most extraordinary implications in all of science, and it follows not from pessimism, but from mathematics. If space is truly infinite, and if matter and energy are distributed throughout it in the roughly uniform way our observations suggest, then the number of possible physical configurations in any given region of space is very large but ultimately finite. Quantum mechanics places limits on the distinguishable states of any physical system. A region of space can only contain so many particles, arranged in so many ways, before the configurations begin to repeat. In a finite region, this means a finite number of possible states. But in an infinite universe, there are infinitely many such regions. And this leads to a conclusion that sounds like something from a dream and is, in fact, a straightforward consequence of the mathematics. In an infinite universe, every possible arrangement of matter that can exist, does exist. Somewhere, separated from you by a distance so vast it would take more digits to write than there are atoms in the observable universe, there is a region of space where the configuration of particles is identical to the one that makes up everything within your observable horizon. The same galaxies. The same stars. The same planet. The same room. The same person, lying in the same position, thinking, in whatever language they have, the same thoughts. This is not metaphor. This is not poetry. It is a direct implication of infinite space combined with finite local configurations. If you shuffle a deck of cards infinitely many times, every possible ordering will occur. Not probably, necessarily. Infinity does not permit anything merely possible to remain merely possible forever. In infinite space, the possible becomes, at sufficient distance, inevitable. The nearest such copy, your nearest identical twin, in a region of space indistinguishable from your own, is estimated to be on the order of 10 to the power of 10 to the power of 28 meters away. A number so large that the observable universe is invisible within it, a single quantum of nothing in a space too vast to picture. But in an infinite universe, that distance is just a distance. It does not represent rarity. It represents location. Beyond that copy, at further distances still, are regions where history diverged slightly, where the same particles arranged themselves differently, where choices went another way, where different outcomes unfolded from the same initial conditions. And then copies of those, and variations of those, and variations of the variations, every permutation played out somewhere in the silent dark, with no audience, no connection, no knowledge of the others. An infinite universe does not just contain everything that is. It contains everything that could be. Every story that the laws of physics permit has been told, somewhere, in the unreachable vastness of an endless space. You are here, in this particular arrangement, in this particular moment. And the universe, if it is truly infinite, has made room for every other version of this moment as well, in all the directions that have no end, in all the silence beyond the last horizon, in all the space that has no outside and no edge and no final word. We ended last time at the edge of something vast. The idea that in an infinite universe, every possible arrangement of matter plays out somewhere, that copies exist, that variations exist, that the full library of physical possibility is not just imagined but instantiated, silently, across an expanse that has no limit. Now it is worth following that idea a little further, because its implications do not stop at the merely astonishing. They continue into territory that quietly dismantles some of our most basic assumptions about what it means to be here at all. Consider the feeling of uniqueness. Not in a sentimental sense, but in a physical one. The specific arrangement of atoms and energy that constitutes you, your body, your brain, the particular configuration of neurons holding whatever thought is passing through your mind right now, feels singular. It feels like a one-time event. Something that happened once, in one place, and will not happen again. In a finite universe, that intuition has some basis. The number of possible configurations of matter in a region the size of your body is staggeringly large, so large that the probability of the same arrangement occurring twice, by chance, within any observable region, is effectively zero. You are, in any practically measurable sense, unique. But infinity is not practically measurable. And in an infinite universe, the logic of uniqueness simply does not hold. We established that the number of distinct quantum states in any bounded region of space is finite. This is not an approximation, it follows from the physics of information and the discrete nature of quantum mechanics. A region can hold only so much information. Matter can only be arranged in so many distinguishable ways. And if the number of possible configurations is finite, and the number of regions in an infinite universe is infinite, then every configuration must repeat. Not occasionally. Not rarely. Infinitely many times. What this means, stated plainly, is that there is no such thing as a unique physical object in a truly infinite universe. Every arrangement of matter that exists anywhere exists infinitely often, scattered across the unreachable dark at distances that dwarf any scale we have discussed. Your particular configuration, the one that reads as you to any physical measurement, is not singular. It is one instance of a pattern that recurs, without limit, across infinite space. This is not a comfortable thought. It is the kind of idea that resists emotional processing, because we are not built for it. Every instinct we have points towards singularity, toward the sense that this moment, this body, this particular version of experience is happening once, and that its onceness is part of what gives it weight. Infinity does not negotiate with that instinct. It simply renders it, in the strictest physical sense, incorrect. And there is a further step. Not only does your configuration repeat, so does every variation of it. Every version of your life in which a single particle somewhere in your body occupied a slightly different position. Every branching of every decision, every alternative history, every outcome that was physically possible given the laws of nature, all of it is represented, somewhere in an infinite universe, in a region physically identical to yours up to that single point of divergence and different afterward. In this framework, weirdness is not a minority condition. Strangeness is not rare. The configurations we would call improbable, unlikely, extraordinary, they are not outnumbered by the ordinary ones. In infinite space, every type of configuration exists infinitely often. The strange and the familiar are equally common, equally distributed, equally real. Infinity erases the hierarchy of likelihood. Everything that can happen is not merely possible, it is, in the fullest sense, happening, somewhere, right now. The universe, in this picture, is not mostly ordinary with pockets of the unusual. It is everything at once, in equal infinite measure, spread across a space too large for the concept of majority to apply. And then there is the question of where you are in all of this. If there are infinitely many copies of you, identical in every physical detail up to this moment, then the question of which one you are becomes genuinely strange. Not philosophically strange in a vague way, but technically strange in a way that physicists and philosophers of probability have struggled to formalize. If every copy has the same memories, the same sensations, the same internal experience of being exactly here, then there is no measurement you could perform, no observation you could make, that would distinguish your location from any other. You cannot point to your copy number. You have no coordinates relative to the others. You are, in the language of probability theory, uncertain about your own self-location in a way that cannot be resolved. This is called the self-location problem, and it is one of the places where the mathematics of infinite universes runs into genuine conceptual difficulty. Probability, as a tool, works by comparing outcomes within a defined space of possibilities. But in an infinite universe with infinitely many identical observers, the space of possibilities does not have a well-defined size. The fractions do not resolve. The probabilities lose their usual meaning. The question of how likely you are to be this particular copy, rather than any of the infinite others, has no clean answer. Some physicists find this troubling enough to use as an argument against the physical reality of infinity. Others accept it as a feature of a framework they are still learning to navigate. Either way, it is a reminder that infinity, when taken seriously, does not merely add more of what we already have. It changes the rules. And now the story takes one more step. Because everything we have discussed so far has been, in a sense, a warm-up for the place where infinity and quantum mechanics meet. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions match experiment to extraordinary degrees of accuracy. And its central feature, the thing that separates it most sharply from classical physics, is that at the smallest scales, the universe does not deal in certainties. It deals in probabilities. Before a quantum measurement is made, a particle does not have a definite position, or a definite spin, or a definite energy. It exists in a superposition, a combination of multiple possible states, each with an associated probability. When a measurement is made, one outcome is observed. The superposition appears to collapse to a single result. And the probability of each outcome is given by a rule called the Born rule, which relates the mathematical description of the quantum state to the likelihood of each possible observation. This rule works. Experimentally, beyond any doubt, it works. If you prepare a particle in a certain state and measure it 1,000,000 times, the distribution of outcomes matches the Born rule with extraordinary precision. But the rule itself, the reason it holds, the mechanism behind it, is one of the deepest unresolved questions in the foundations of physics. Now bring infinity into this picture. In a truly infinite universe, every quantum measurement that has ever been made, every interaction, every decay, every collision between particles, has played out across all of space simultaneously. Not in the sense of a signal traveling outward, but in the sense that the initial conditions of an infinite universe, combined with the same physical laws operating everywhere, would have produced every quantum outcome, somewhere, in some region of infinite space. Think about what this means. When a particle decays, we observe one outcome. But in the infinitely many identical experimental setups distributed across infinite space, every possible outcome of that decay is realized, an equal physical fact, in some region. The outcome you observe is not the only one that happened. It is the one that happened here, in this particular region, in this particular copy of the experiment. Elsewhere, the other outcomes occurred, in identically prepared systems, with equal physical reality. In this framing, the Born rule, the probability rule at the heart of quantum mechanics, takes on a new interpretation. It is no longer just a rule for predicting what you will observe. It becomes a statement about the distribution of outcomes across infinite space. When we say that a quantum event has a 25% probability of one outcome and a 75% probability of another, we might be saying something about how those outcomes are distributed across an infinite ensemble of identical experiments. 3/4 of the copies will see one result. 1/4 will see the other. Not randomly, deterministically, according to the physics, but distributed across the infinite variety of positions that infinite space provides. This is a genuinely different way of thinking about what probability means in physics. And it has a name, or rather, several names, depending on who you ask, but the core idea is sometimes called the many worlds interpretation of quantum mechanics, or the Everett interpretation, and it is taken seriously by a significant number of physicists, not as a curiosity, but as a coherent framework for understanding why the Born rule works. In this view, there are no truly random events. There are only outcomes, all of which occur, distributed across the branches of a wave function that encompasses all of space and time. What feels like chance, the moment of uncertainty before a measurement resolves, is simply the moment before you discover which branch, which region, which version of the infinite stage you happen to be standing on. All outcomes happen. The question is only which one is local. And in an infinite universe, that question, which one is local, which version is mine, is not a question about what is real. Everything that can happen is real, somewhere in the unreachable expanse. The particle decays both ways. The outcome resolves in every direction. The universe does not choose. It simply contains all of it, all at once, in the boundless, patient, indifferent space that has no edge and no center and no final word on anything. There is a kind of strange peace in that, if you let yourself reach for it. Not the peace of resolution. The peace of completeness. Of a universe so large that nothing is left out. Every possibility honored. Every outcome housed. Every version of every moment given its place in the silent, endless dark. Quantum mechanics and infinity make uncomfortable companions. Separately, each is already demanding. Quantum mechanics asks us to accept that particles do not have definite properties until measured, that probability is woven into the fabric of reality at its finest scale, and that the act of observation is not a passive recording but an active participant in determining what is found. Infinity asks us to accept that space has no end, that every configuration of matter recurs, and that uniqueness, in the physical sense, is an illusion maintained only by the smallness of what we can see. Together, they produce something that even the most rigorous physicists have found genuinely difficult to untangle. We touched last time on the idea that in an infinite universe, every quantum outcome is realized somewhere. But it is worth slowing down and following that thought more carefully, because it leads somewhere unexpected. In standard quantum mechanics, the history of a particle between measurements is not a single definite trajectory. It is, in a precise mathematical sense, a sum over all possible histories, every path the particle could have taken, weighted by probability, contributing to the final outcome. This formulation, developed by Richard Feynman, is not a metaphor. It is the actual calculational machinery that produces correct predictions. The particle, in some sense, takes all paths simultaneously, and the interference between those paths determines what we observe. In a finite universe, these histories are abstractions, tools for calculation, not necessarily literal descriptions of separate realities. But in an infinite universe, every one of those histories has physical space to be real. Every path the particle could have taken is taken, somewhere, in some region of infinite space where the initial conditions were identical and the quantum branching went differently. The sum over histories is not just a mathematical device. It is a map of infinite physical actuality. And quantum fluctuations, those small, spontaneous variations in energy that quantum mechanics says must occur in any region of space, even a perfect vacuum, also take on a different character in infinite space. In any finite region, quantum fluctuations are small. They are temporary. They create and destroy virtual particles on timescales too brief to observe directly, and their average effect is accounted for in the structure of physical law. But over infinite space and infinite time, these fluctuations cover every magnitude, every scale, every degree of intensity. In an infinite universe with infinite time available, quantum fluctuations will, with certainty, occasionally produce, by pure chance, a large, coherent structure out of the random churning of the vacuum. This leads to one of the most philosophically uncomfortable ideas in all of modern physics. It is called the Boltzmann brain. The physicist Ludwig Boltzmann, working in the 19th century, was concerned with a different but related problem, the statistical nature of entropy and the arrow of time. His insight was that in a sufficiently large and sufficiently old universe, random thermal fluctuations could, in principle, spontaneously assemble any ordered structure, however complex. The probability is vanishingly small for any given moment in any given region. But given infinite time and infinite space, even vanishingly small probabilities become certainties. And the most probable complex structure that could arise spontaneously from a quantum or thermal fluctuation is not a galaxy. It is not a planet, or a civilization, or a brain growing inside a body that evolved over billions of years. The most probable complex structure is the smallest one capable of having a conscious experience, a single, isolated brain, momentarily fluctuated into existence, containing a full set of memories that feel real but have no causal history, experiencing one brief moment of awareness before dissolving back into randomness. In an infinite universe with infinite time, such Boltzmann brains would be produced in incomprehensible numbers. And here is the uncomfortable implication: if they are produced infinitely often, and if ordinary observers like us are produced only finitely often, or at a much lower rate, then the overwhelming majority of conscious observers in an infinite universe would be Boltzmann brains. Momentary fluctuations. Isolated sparks of apparent experience with no genuine past. Which raises a question that is difficult to dismiss once you have heard it. How do you know you are not one? You have memories. You have a sense of continuity. You have the feeling of having lived through a sequence of events that led to this moment. But a Boltzmann brain, by definition, would have all of those things as well, assembled from quantum noise into a configuration that includes a complete and internally consistent set of false memories. There is no internal measurement you can perform that would distinguish genuine history from a fluctuated simulacrum. Most physicists do not believe we are Boltzmann brains. The standard response is that a physical theory predicting most observers are Boltzmann brains is probably a flawed theory, and that we should look for frameworks that make ordinary observers typical rather than extraordinarily rare. But the fact that this argument is needed at all, that it is a live concern requiring active theoretical management, tells you something about the seriousness of what infinity introduces when combined with quantum mechanics. And this brings us to what may be the deepest technical problem in the physics of infinite universes. It is called the measure problem, and it has resisted solution for decades. Probability, at its core, is a counting exercise. You count the number of ways a desired outcome can occur, divide by the total number of possible outcomes, and the result is the probability. This works cleanly when the number of outcomes is finite. When you roll a die, there are 6 outcomes. When you draw a card, there are 52. The mathematics is well defined because the set is bounded. In an infinite universe, there are infinitely many outcomes of every kind. Infinitely many regions where you exist. Infinitely many where you do not. Infinitely many where a particular quantum event went one way, and infinitely many where it went another. When you try to form a ratio, to ask what fraction of observers are in such and such a situation, you are dividing one infinity by another, and the result is undefined. Not approximately undefined. Rigorously, mathematically undefined. The measure problem is the problem of making sense of probability in this context. Of finding a way to compare infinite sets of outcomes in a manner that gives consistent, physically meaningful answers. Several approaches have been proposed. Some weight outcomes by the volume of space they occupy. Others weight by the number of observers. Others use temporal cutoffs, imagining a surface of constant time and counting outcomes up to that point, then taking a limit as the cutoff is pushed to infinity. Each approach has been explored seriously, and each has been found to produce results that are, in some cases, deeply counterintuitive or inconsistent with observation. No fully satisfactory solution has been found. The measure problem is not a minor technical issue waiting to be cleaned up. It is a fundamental conceptual gap, a place where our tools for reasoning about probability break down completely, and no agreed replacement has yet been constructed. This has consequences for how we think about typicality. In science, and in everyday reasoning, we rely on the assumption that we are, in some sense, typical observers. If you wake up and find the laws of physics working normally, you conclude that the laws of physics generally work normally, not just here, not just today, but as a general rule. This inference depends on the assumption that your situation is representative of the broader class of situations that observers find themselves in. But in an infinite universe with a broken measure, typicality has no clean meaning. If you cannot define what fraction of observers are in a given situation, you cannot say whether your situation is typical or rare. You cannot reason from your own experience to conclusions about the universe at large. The inferential bridge that connects personal observation to universal law, the bridge that all of science ultimately stands on, becomes uncertain in ways that are difficult to repair. The typical observer problem asks, given that you exist, and given that you are making observations, what can you infer about the kind of universe you are likely to inhabit? In a finite universe, this question has manageable answers. In an infinite one, it becomes entangled with the measure problem and loses its footing. Some cosmologists have argued that this is a reductio ad absurdum, that the fact infinity leads to these conclusions is itself evidence that the universe is not actually infinite, that some physical mechanism must eventually bound the total extent of space. Others argue that the problems are real but soluble, that the right measure theory has simply not been found yet, and that infinity should not be abandoned merely because it is difficult. What both sides agree on is that infinity, in physics, is not free. It does not come without cost. Every time you write the symbol for infinity into your model of the universe, you are implicitly accepting a package of consequences that extends far beyond what the symbol itself suggests. You are accepting Boltzmann brains and self-location uncertainty and broken probability and the measure problem and the end of typicality as we understand it. These are not small things to accept. They are not background details. They are challenges to the foundations of how we reason about the world, challenges that remain, for now, genuinely open. And perhaps that is the appropriate note on which to let this section rest. Not a conclusion, but an opening. Not the satisfying click of a solved problem, but the larger, quieter sound of a question that has grown bigger the more carefully it has been examined. Infinity is not just a feature of the universe we happen to live in. It is a test of our mathematics, of our logic, of the limits of what minds like ours can hold. And the fact that we can pose the question at all, that we can follow the argument this far, that we can sit with the discomfort of not knowing what probability even means at the largest scales, that, in itself, is something worth noticing. You are a finite thing, in what may be an infinite space, asking questions that your own mind was not built to fully answer. And somehow, that seems exactly right. There is a point in any serious engagement with infinity where ordinary language simply stops working. Not because the ideas are too complex to explain, but because the words themselves were built for a different scale. Words like vast, enormous, boundless, they gesture toward large things, things that exceed ordinary experience. But they still carry the flavor of the finite. When you call something boundless, there is still an implicit somewhere at the center of the description, a speaker standing inside the experience of largeness, gesturing outward. Infinity doesn't allow that. It has no center from which to gesture. It contains the speaker as thoroughly as it contains everything else, and the usual tools of emphasis and scale simply dissolve. This is not just a literary problem. It is a technical one. When physicists try to reason carefully about infinite universes, they find that the standard vocabulary of science, more, less, typical, rare, likely, unlikely, begins to fail in the same way. An infinite universe does not have a majority. It does not have a representative sample. It cannot be surveyed. It resists every instrument we have developed for comparing quantities, because all of those instruments assume, somewhere in their foundations, that the thing being measured has a finite size. Information is a useful lens here. Modern physics treats information with the same seriousness it treats energy or matter, as a fundamental quantity, subject to conservation laws and physical limits. In any bounded region of space, the total amount of information that can be stored is finite, determined by the region's surface area in a relationship described by the Bekenstein bound. This means that any finite volume of space has a finite number of distinguishable states, which is part of what makes the argument for repeating configurations in an infinite universe so rigorous. But across infinite space, the total information content is infinite. And infinite information is not just a lot of information. It is a category that breaks the usual tools of information theory. You cannot compress it. You cannot transmit it. You cannot take a representative sample and reason from the part to the whole, because in an infinite set, no finite sample is ever representative in the strict sense. The part is always measure zero compared to the whole. We are, in a real sense, finite minds attempting to process a concept that generates infinite data. And the honest response to that is not to pretend the tools work when they don't, but to acknowledge the limit and continue anyway, carefully, humbly, with appropriate uncertainty about how much of what we think we understand is genuine insight and how much is the familiar feeling of a map that doesn't quite match the territory. Now, if a single infinite universe already strains the boundaries of what we can reason about, there is a framework in modern cosmology that adds another layer entirely. It begins with a feature of the inflationary model that was not initially expected. Inflation, that period of extraordinarily rapid expansion in the early universe, may not have been a single, uniform event that happened once and then stopped. In many versions of inflationary theory, inflation is not naturally self-terminating. Once it begins, it tends to continue, driven by a quantum field whose energy keeps the expansion accelerating. In most regions, this field eventually decays, inflation ends, and a hot, dense universe like ours is produced. But quantum fluctuations mean that in some regions, the field does not decay. It keeps inflating. And as those regions expand, they produce yet more volume, which may itself partially decay into new universes while the rest continues to inflate. This process, once it begins, does not stop. It is self-sustaining, self-reproducing, generating new regions of post-inflationary space at a rate that outpaces any local ending. It is called eternal inflation, and its implication is as large as the name suggests. If eternal inflation is correct, our universe, the entire observable universe and everything beyond our horizon, the full infinite extent of space as we have been discussing it, is just one bubble. One region where inflation happened to end and a particular set of physical conditions settled into place. And surrounding it, on scales that bear no meaningful relationship to anything we can measure, inflation continues. An endless churning sea of expanding space, punctuated by bubble after bubble, each one a universe in its own right, each one potentially vast, each one potentially with its own physical laws, its own constants, its own character. This is the multiverse. Not in the casual sense the word is sometimes used, but in the precise cosmological sense, an infinite ensemble of post-inflationary regions, produced by an eternally inflating background, each one causally isolated from all the others, collectively representing a space of physical possibilities so large that the word everything begins to seem inadequate. And here the problems multiply again, because if eternal inflation produces all possible universes, if every combination of physical laws and constants that is consistent with some underlying theory is realized, somewhere, in some bubble, then we are back in the territory where probability breaks down. The same measure problem that afflicts a single infinite universe now afflicts an infinite collection of universes. How do you compare the number of bubbles where one set of constants holds to the number where another set holds, when both numbers are infinite? The problem of all possible universes is not just a numbers problem. It is a question about what it even means for something to be possible. In a framework where every physically consistent configuration is realized somewhere, the distinction between what exists and what could exist collapses. The possible and the actual become the same thing. And if everything possible exists, then the concept of possibility has changed its meaning, from a statement about what might happen, to a statement about what is already, somewhere, the case. Some physicists find this liberating. Others find it corrosive to the project of science. If every set of physical laws is equally real somewhere, then why do we have the laws we have? What does it mean to explain our constants if every other value of those constants is equally instantiated elsewhere? Explanation, in science, traditionally means showing why one thing is the case rather than another. In a framework where all things are the case, that structure of explanation may not apply. Which leads, by a natural path, to one of the most debated ideas in modern physics, the anthropic principle and the question of fine-tuning. The physical constants that govern our universe, the strength of gravity, the mass of the electron, the cosmological constant that determines the energy of the vacuum, appear, to a degree that many physicists find striking, to be calibrated to permit the existence of complex structures. Change any of them by a small amount, and the universe becomes inhospitable to atoms, or to stars, or to the long-lived stable conditions under which chemistry and life can develop. The cosmological constant, in particular, is famously precise. Its observed value is so much smaller than theoretical calculations might naively predict that its smallness has been called the worst fine-tuning problem in physics. One response to this observation is to look for a deeper physical principle that explains why the constants have the values they do, a theory so fundamental that the constants are not free parameters but necessary consequences. This is the dream of a final theory, and it has not yet been achieved. Another response, the anthropic one, is to argue that in an infinite universe, or an infinite multiverse, the question of why the constants are what they are is not a question about unique necessity. It is a question about selection. If infinitely many regions exist with infinitely many combinations of constants, then most of those regions will not permit the development of observers. The regions where observers can exist are, by definition, the regions where the constants fall in the range compatible with complexity. And any observer asking the question, "Why do the constants permit my existence?" is necessarily in one of those rare compatible regions. The answer to the question is already contained in the fact that the question is being asked. This is the anthropic argument, and it is genuinely controversial. Critics point out that it does not predict anything specific, that it can accommodate almost any observation by noting that observers must be somewhere, and wherever they are, the conditions will look suitable. It risks replacing explanation with selection, and some physicists feel this is a step backward from the goal of genuine understanding. Supporters argue that in a framework where many universes genuinely exist, the anthropic selection is a real physical effect, as legitimate as any other selection bias in science. When you observe that a hospital contains sick people, you are not discovering something profound about the nature of illness, you are observing a selection effect. The hospital is where sick people go. Similarly, an observer will always find themselves in a universe compatible with observers, not because the universe was designed for them, but because the incompatible ones contain no one to notice. The debate has not been resolved. It may not be resolvable, for reasons that circle back to everything we have discussed: the measure problem, the inaccessibility of other regions, the difficulty of making predictions in infinite ensembles. But the conversation itself is revealing. It shows that the question of why anything is the way it is, why these constants, why this universe, why conditions suitable for complexity and consciousness and quiet evenings spent wondering about space, is a question that infinity transforms rather than answers. In a single finite universe, fine-tuning is a deep mystery demanding a deep explanation. In an infinite universe or multiverse, fine-tuning dissolves into selection, not explained exactly, but recontextualized. The mystery doesn't disappear. It changes shape. And perhaps that is the most honest thing to say about all of this. Infinity does not resolve our questions about existence and meaning and why anything is the way it is. It reframes them. It takes the questions we thought were about this universe and reveals them to be questions about a vastly larger space of possibilities, a space we cannot observe, cannot fully reason about, and cannot step outside of. We are, each of us, in a bubble. Whether that bubble is one universe among infinitely many, or simply one life among the vastness of a single infinite cosmos, the essential condition is the same. We see what we can see from where we are. We reason as carefully as we can with the tools we have. And beyond the horizon of what we can reach, the rest of whatever exists continues, in whatever form it takes, with or without anyone to notice. There is something in that which feels, on reflection, less like a loss than like a release. The universe is not obligated to be the size of our understanding. And the fact that it so thoroughly exceeds it, that it keeps exceeding it, layer after layer, scale after scale, each answer opening into larger questions, is not a failure of knowledge. It is the shape of a reality that has more in it than any finite mind was built to hold. And we keep looking anyway. quietly. From our small, improbable place in the middle of all of it. There is a question that has puzzled astronomers since the 18th century, and it goes by the name of a German physician who thought carefully about the night sky and found something in it that didn't add up. Heinrich Olbers observed, with elegant simplicity, that if the universe is infinite and uniformly filled with stars, then every line of sight from any point should eventually terminate on the surface of a star. Not after a long journey, not after passing through empty space. Eventually, in an infinite and eternal universe, every direction you look should end in starlight. The night sky, by this logic, should be as bright as the surface of the sun in every direction. Blazing. Uniformly luminous. Impossible to distinguish night from day. And yet the sky is dark. This is Olbers' paradox, and its resolution tells a compact version of the entire cosmological story we have been tracing. The sky is dark at night because the universe is not infinitely old. Because light has a finite speed. Because the universe is expanding, which stretches and dims the light from distant sources. Because there is a horizon, and beyond it, no signal has yet arrived. The darkness of the night sky is, in a precise sense, evidence for the Big Bang, evidence that the universe had a beginning, that it has been expanding ever since, and that we live inside a finite bubble of received information surrounded by the unreachable dark. But Olbers' paradox also does something else. It shows that even in a universe that may be spatially infinite, silence is possible. Emptiness is possible. The infinite extent of space does not guarantee an infinite flow of information or energy or light. What we receive is bounded by time and by the speed at which information can travel. The silence of the universe is not the silence of emptiness. It may be the silence of everything that hasn't arrived yet, or everything that never will. And in that silence, a deeper worry sometimes surfaces. It is less a scientific problem than a philosophical one, but it presses on the practice of science from below. If the universe is truly infinite, if it contains, beyond our horizon, regions we can never observe and events we can never measure, then there is a sense in which naturalism itself, the project of explaining the world through discoverable physical laws, runs into a boundary it cannot cross. Naturalism depends on the assumption that the universe is, in principle, comprehensible. That its regularities can be found, described, tested, and extended. That explanation is always possible, even if not yet achieved. But in a framework where infinite regions lie permanently beyond any experiment, where the full structure of reality can never be mapped, where the measure problem undermines probability and the self-location problem undermines inference, the project of complete explanation may be not just practically difficult but structurally impossible. This is sometimes called the end of explanation worry, the concern that infinity, taken seriously, places a permanent ceiling on what science can achieve, not because of technological limits but because of the geometry of the knowable. There will always be more universe than any map can contain. There will always be questions whose answers, if they exist, lie beyond the last horizon. The scientific project may be, in a deep sense, infinite, not in the sense of endless progress, but in the sense of endless remainder. Some philosophers find this troubling. Others find it clarifying. The distinction between what can be known and what exists is, after all, one of the oldest in human thought. The world is not obligated to be fully accessible. And acknowledging the limits of what science can, even in principle, decide is not a retreat from rationality. It is an expression of it. There are questions about the universe that are, in the technical sense, undecidable. Not unknown, undecidable. Questions for which no experiment, however sophisticated, could in principle return a definitive answer. Whether the universe is truly infinite is one of them. Whether space has a topology that wraps around at scales beyond our horizon is another. Whether other bubble universes exist in an eternally inflating background is a third. These are not questions awaiting better telescopes. They are questions that the causal structure of our universe may permanently place outside the reach of empirical resolution. This is a significant thing for science to admit. Not a shameful thing, a significant one. It means that the map of the knowable has edges. Not vague, distant edges that recede as we advance, but fixed structural boundaries built into the physics. Beyond a certain horizon, the universe stops sending letters. What remains on this side of the boundary is still extraordinary. The observable universe contains hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars. The complexity of chemistry, biology, geology, atmosphere, and mind that has emerged within a single solar system over 4.5 billion years is enough to occupy scientific inquiry for centuries more. The questions we can answer are not running out. The job is not nearly done. But it is an infinite job. Not in the discouraging sense of a task that never progresses, but in the sense of a horizon that always extends. Every answered question reveals new questions behind it. Every layer of explanation rests on a deeper layer not yet reached. The universe appears to be, at every scale we examine, more intricate than the scale above it suggested. More structured, more subtle, more richly connected. And this is true even on the very largest scales. Even in the context of everything we have been discussing, the infinite extent of space, the multiverse, the breakdown of probability, the permanent darkness beyond the causal horizon, the universe as we observe it, within the bubble we inhabit, continues to reward attention with beauty. One of the most important clarifications to carry through all of this is something easy to miss. Infinite space does not mean infinite energy density. It does not mean infinite temperature, or infinite mass per unit volume, or infinite anything in the local physical sense. The universe, for all its spatial extent, is extraordinarily dilute. The average density of matter in the observable universe, averaged across all the vast empty regions between galaxies, is roughly equivalent to a few hydrogen atoms per cubic meter. A near-perfect vacuum, on any human scale. The infinite is, predominantly, empty. This matters because it separates two ideas that are easy to conflate. A universe that is infinite in extent is not a universe that is infinite in intensity. The space between galaxies is cold and dark and almost featureless. Even within galaxies, the distances between stars are so large that the night sky, seen from interstellar space, would be only marginally brighter than the one we see from Earth. The universe is mostly nothing, with thin threads of something woven through it, and those threads, extraordinary as they are, do not fill the infinite void. They decorate it. There is something in this that feels, at the end of a long journey through large ideas, almost comforting. The infinite is not overwhelming in a physical sense. It does not crush or blind or overfill. It extends, quietly, in all directions, mostly dark, mostly still, mostly patient, and here and there, in thin concentrations separated by distances that make the word far seem small, something happens. A star ignites. A planet forms. Water flows. Something stirs. The universe does not need infinite energy to be infinite in extent. It needs only space, and time, and the quiet persistence of physical law across every region it contains. The same rules, everywhere. The same darkness between the lights. The same patient expansion, carrying everything gently apart, while gravity holds the local things together just long enough for complexity to try. We are one of those local things. A brief concentration of atoms in a cold and mostly empty cosmos, capable, somehow, of asking what the cosmos is. Of following the question as far as it goes. Of sitting with the answers that aren't really answers, and finding that something about the sitting is worthwhile. The universe does not appear to know that we are here. It does not orient toward us, or respond to our questions, or offer the satisfaction of a final explanation. It simply continues, in every direction, at every scale, through every moment, doing what it does, according to the same laws it has always followed, in a space that may have no end. And we are in it. Finite and temporary and genuinely here, in the middle of something immeasurably large, with minds just capable enough to sense the scale of what we cannot grasp. That is not nothing. That is, depending on how you hold it, almost everything. The questions will still be there tomorrow. The horizon will not have moved. The darkness beyond it will remain exactly as unreachable as it was tonight. And somewhere, in the silence between one thought and the next, the universe continues, calm and vast and indifferent and, in its own quiet way, complete. Physics has a habit of producing paradoxes that turn out not to be paradoxes at all, just places where an assumption was hiding that nobody had thought to question. Olber's paradox was one of those. The sky should be bright if the universe is infinite and eternal, and it isn't, and the resolution, finite age, finite light travel time, expanding space, turned out to carry inside it the entire architecture of modern cosmology. But Olber's paradox is not the only place where infinity, applied naively to physical quantities, produces results that seem to demand correction. Apply the same logic to gravity. In a truly infinite, uniform universe, the gravitational pull on any given point from all the matter distributed across infinite space should, by naive calculation, be infinite in every direction simultaneously, an infinite tug from every side, with no resolution. This was a problem that troubled Newton himself, and it took the development of general relativity and the concept of an expanding universe to dissolve it properly. The resolution, again, was not that infinity is wrong, but that the framework being used to calculate was missing something essential. The expansion of space, the finite age of the universe, the way gravity actually behaves in a relativistic cosmos. All of these change the calculation in ways that remove the paradox without requiring space to be finite. The pattern is worth noticing. Again and again, infinity applied to the wrong variables in the wrong framework produces nonsense. And again, the resolution is not to remove infinity from the picture but to refine the picture, to understand which quantities are genuinely infinite, which are finite, and which are simply undefined in ways we have not yet learned to handle. Photons offer a particularly beautiful example of this refinement. A photon, once emitted, travels at the speed of light. And from the perspective of special relativity, from the photon's own reference frame, if we can speak loosely of such a thing, no time passes at all. The photon does not experience a journey. For a particle moving at the speed of light, the distance it traverses and the time it takes to traverse it are both, in the relativistic sense, zero. It is emitted and absorbed in what is, from its perspective, a single instant. This means that a photon released in the early universe, one of the ancient photons of the cosmic microwave background, say, traveling for nearly 14 billion years before entering a radio telescope on Earth, has, in its own frame, experienced no time whatsoever. It is, in a precise relativistic sense, eternal. Not long-lived. Not ancient. Eternal, outside of time entirely, existing in a kind of frozen present that encompasses the whole of its journey from emission to absorption. In an infinite universe, photons travel indefinitely unless absorbed. Some fraction of the light emitted by every star in every galaxy will, if the universe is infinite and if space continues to expand, travel forever, never finding an absorbing surface, redshifting gradually toward longer and longer wavelengths, growing colder and more diffuse, but persisting. The universe, in this sense, is threaded with light that will never arrive anywhere. Eternal travelers moving through infinite space, carrying energy that diminishes toward nothing but never quite becomes nothing in any finite interval of time. It is a strange kind of permanence. Not the permanence of a solid thing sitting in one place, but the permanence of motion, of something that continues simply because nothing has yet stopped it, and in an infinite universe, nothing ever will. This connects to one of the deepest revisions that modern physics asks us to make to an everyday concept, the concept of nothing. In ordinary experience, nothing means empty. The absence of things. A vacuum is nothing. A dark room with no air and no light and no detectable anything would seem, intuitively, to qualify as nothing. But quantum mechanics is unambiguous on this point. There is no such thing as true emptiness. The vacuum is not nothing. It is a quantum field in its lowest energy state, a state that still contains fluctuations, still carries energy, still produces virtual particles that flicker in and out of existence on timescales too brief to measure directly, but whose effects are observable in careful experiments. The Casimir effect, for instance, the measurable force between two uncharged metal plates placed very close together in a vacuum, arises directly from the quantum fluctuations of empty space. The vacuum pushes. The nothing does something. And in quantum field theory, the vacuum is not a passive background against which events occur. It is an active participant, structured, energetic, and far from featureless. In an infinite universe, this quantum vacuum extends everywhere. Every cubic meter of what looks like empty space is, at the quantum scale, a seething structure of virtual activity. Not visible, not directly measurable in most circumstances, but physically real in its effects. The infinite universe is not filled with nothing. It is filled, everywhere, with the restless quantum ground state of every field that exists, and what we call emptiness is only the calm surface of something considerably more intricate beneath. There is also a granularity to nature at the smallest scales that sits in interesting tension with the smoothness we usually attribute to infinite space. Quantum mechanics suggests that space and time may not be infinitely divisible, that below a certain scale, the Planck scale, the concepts of distance and duration may lose their usual meaning entirely. Some approaches to quantum gravity propose that space-time is fundamentally discrete at that level, that there is a smallest possible length, a smallest possible interval of time, and that the apparent continuity of space is a large-scale illusion, like the apparent smoothness of a surface that is, under sufficient magnification, made of atoms. If this is correct, it introduces a curious asymmetry. The universe may be infinite in extent, space may go on without end at large scales, while being fundamentally granular and discrete at small scales. Infinite in the large, finite in the small. An endless expanse of tiny quanta, each one irreducible, each one the smallest possible unit of spatial existence, stretching outward without limit but unable to be subdivided beyond a certain point. The intuitions we carry about space, that it is smooth, continuous, infinitely divisible, the same at every scale, are almost certainly wrong in at least one direction. Nature, it seems, is not obligated to be consistent with the mental images we find most comfortable. And this, perhaps, is the most important lesson that a long, careful engagement with infinity eventually delivers. Our intuitions fail. Not occasionally, not in exotic edge cases, but systematically, whenever we push far enough beyond the scale at which they were formed. The intuition that large things are finite, that every journey has a destination, that empty space is truly empty, that events have unique outcomes, that probability always sums to one, that explanation always terminates somewhere, all of these fail, in specific and demonstrable ways, when applied to the universe at its actual scale. This is not a failure of human intelligence. It is a feature of having intelligence that evolved in a particular environment, on a particular scale, for particular purposes. The cognitive tools that allow us to navigate a world of medium-sized objects at medium speeds and medium-length lifetimes are not the same tools needed to navigate quantum mechanics, or general relativity, or the thermodynamics of eternal expansion, or the topology of possibly infinite space. We have been able to extend our reach into those domains only by building new tools, mathematics, formal logic, carefully designed experiments, and even those tools have limits we are still finding. And yet, there is a sense in which infinity, for all the trouble it causes, carries a certain promise. An unexpected one. In finite, complicated systems, rare things are rare. The probability of a specific configuration decreases as its specificity increases. The more precisely you define what you are looking for, the less likely you are to find it. Rarity has weight. it means something. In an infinite universe, rarity loses that weight. Everything that can occur does occur, not once, not occasionally, but infinitely often. And while this dismantles the concept of uniqueness in one sense, in another sense it simplifies the structure of physical possibility. There is no hierarchy of likelihood at the cosmic scale. No configurations that are forbidden by their improbability, no structures kept from existing by the smallness of their chances. If the laws permit it, it exists. Somewhere. The bookkeeping of possibility is handled by the infinity of space, and the account is always settled. This is, in a strange way, a kind of simplicity. Not the simplicity of fewer things, but the simplicity of no exceptions. An infinite universe is one in which the laws are the complete story. Everything else follows, without remainder, without the need to explain why this happened and that didn't. Everything happened. Every branch was taken. The infinite accommodates all of it without effort. There is also a question that the infinite extent of time, not just space, but time, raises with a particular kind of quiet insistence. It is sometimes called the why this age question. If the universe is infinitely old in the past, or if it will exist for an effectively infinite time in the future, then why do we find ourselves here, at this particular moment? Why this era? In a universe 14 billion years old that may run for trillions or quadrillions more, what selects for observers appearing precisely now? The answer, again, is anthropic in character. Stars, in their current form, exist only during a particular window of cosmic history. Before the first stars ignited, there were no heavy elements, no planetary systems, no chemistry complex enough for life. After the last stars burn out, the conditions for biological complexity will be gone. We exist when we do because we require what this era provides: long-lived stable stars, liquid water, the particular chemistry of a universe a few billion years into its stellar age. The timing is not arbitrary. It is selected by our own requirements for existence. But the question carries a residue that the anthropic answer doesn't fully dissolve. There is still something to sit with in the recognition that this moment, now, this specific sliver of cosmic time, is a vanishingly thin window in the life of what may be an infinite universe. That before and after this window, for durations that make the current age of the cosmos seem brief, there is either not yet the conditions for minds or no longer the conditions for minds. And in that narrow window, against that immense backdrop, something like awareness arose and looked around and asked where it was. As for time travel, one of the great romantic ideas in all of science fiction, the infinite extent of space offers no particular comfort. General relativity permits, in principle, certain solutions to its equations that contain closed time-like curves, paths through space-time that loop back on themselves, allowing a traveler to return to their own past. These solutions exist mathematically. Whether they can be physically realized is a separate question, and most physicists suspect the answer is no, that the universe enforces a kind of chronological self-consistency that prevents the paradoxes time travel would introduce. An infinite universe does not make time machines easier to build. It simply means that if time machines are impossible, they are impossible everywhere, infinitely often, without exception. The vastness of space is not a workaround. The laws of physics travel with you. And this, in the end, brings everything back to a question that was always underneath the cosmology and the mathematics and the quantum mechanics. A question not about the structure of space, but about what it means to be inside it. If the universe is infinite, truly, literally infinite, then it contains infinitely many versions of every moment, infinitely many outcomes of every choice, infinitely many instantiations of every life. Nothing that happens here is unique. Nothing is rare. Nothing is, in the cosmic accounting, a singular occurrence. Every grief is infinitely replicated. Every joy occurs infinitely elsewhere. Every ending is also, somewhere, a continuation. For some people, this thought brings comfort. The sense that nothing is truly lost, that every configuration of the universe is, in the infinite, preserved and reproduced. That the things that matter are not extinguished by the expansion of space or the passage of time, because they are encoded in the structure of a universe that plays out every variation without exception. For others, it brings the opposite. If nothing is unique, does anything matter? If this moment is one of infinitely many identical moments happening simultaneously across infinite space, does the local feel of it, the weight of it, the intimacy of it, mean anything at all? This is the psychological weight of infinity. Not a scientific problem, but a human one. And it is, in some ways, the oldest problem in all of philosophy dressed in the language of modern cosmology. But here's what the universe, for all its silence on the subject, seems to offer when you look carefully. The infinite does not diminish the local. The fact that your configuration recurs across infinite space does not reduce the reality of this instance of it. The grief is real here. The warmth is real here. The particular way this moment feels, the specific texture of it, in this body, in this place, in this sequence of thoughts, is not made less real by the existence of other instances of it elsewhere. Reality is not diluted by replication. The infinite does not thin out what happens here. In fact, if anything, the infinite provides a strange kind of permission. Permission to find the local meaningful precisely because meaning is not a cosmic quantity, not something allocated by the universe from a finite supply. Meaning is what happens when a mind that is capable of caring is present to what is occurring. In that capacity, caring, attending, finding some things more important than others, is not a feature of the infinite. It is a feature of the finite, of the small, of the particular. You are a finite arrangement of matter in an infinite space, and you are the only part of that infinite space that is, right now, thinking about it. Not the only instance, but the only one that is here. The only one that is this. The universe may go on without end. Time may run forward into darkness and silence and the slow exhaustion of every gradient that makes events possible. Space may contain infinitely many versions of this moment, this life, this small bright spark of awareness. And none of that changes what is happening right now, in the only place you actually are. Here. This. Still.